Hello, this is a demonstration and a discussion on the working principle of one of our experiment of the diffraction of light by ultrasound. C.V. Raman and Raman-Nath, they had significant contribution in the explanation of how it works, the diffraction of light by ultrasound, so much so that often we call this effect as Raman-Nath effect. That the light can be diffracted by acoustic waves, the standing waves of ultrasound, that was first demonstrated by Debye and Sears in 1932. So what they did is they took a box full of liquid, let's say water, and then at the one side of this rectangular box they put a ultrasound head, which is like a speaker, makes a ultrasound, very high frequency sound, much beyond 20 kilohertz. We can't hear it, of course. Now these acoustic waves inside the box, they create a set of standing waves. So we have alternate layers of high density and then low density and then high density and low density. So density changes periodically along the length of the box. Now, refractive index being a function of density, it also changes periodically. So we have regions of high refractive index, then region of low refractive index, then again region of high refractive index. So it's a periodic modulation of the refractive index of the liquid happening because of the standing wave of the ultrasound. Now suppose we send light through one of the side of the box. Okay. So light passes through the box and emerges on the other side. So as it happens, you can clearly understand that sometimes the light ray passes through a region of high refractive index, and then next ray passes through a region of low refractive index, then again another ray which is passing through a region of high refractive index. So as such, if the light ray had a flat wavefront before it entered the box, after it passes through the box, it has a corrugated wavefront. So the phase of the light is different depending on where it has passed through. For example, after it passed through a high density, high refractive index region, it will have certain phase. The next region, which is low refractive index, will have a different phase. So light phase, if we could monitor that, we will see that it has a alternately or rather periodic variation of the phase in the wavefront, and we call it the corrugated wavefront. Now this corrugated wavefront, if you take into account contribution of each point in producing intensity on a faraway screen, which we show it here, and if you essentially need to integrate over it. If you do that, then you get periodic variation and you get intensity like a diffraction pattern, well separated maxima and minima of different order. Now this was first discussed by Debye and Sears, but this corrugated wavefront, that concept came from Raman and Nath. To analyze that, what they did is they wrote down the amplitude of the light, which is a function of time and position, as the amplitude, and then exponential I omega t, omega being the angular frequency of the light, t is the time, minus 2 pi by lambda. Lambda is the wavelength of the light, and L is the amount it has traversed. So, L is the length of the box. So after the length of the box, you expect the amplitude to be this much. Except this lambda is lambda naught, which is the wave function, wavelength of the light divided by the refractive index. Now refractive index changes as a function of the position. Here x means this vertical direction. So depending on where the light is passing through the liquid, we will have a different refractive index. So refractive index is a periodic function of x being vertical again. So as such, we can write the refractive index as some average value mu naught minus an amplitude, and a sinusoidal function of x, twice by x by lambda s. Now this lambda s is essentially the wavelength of the ultrasound. So the ultrasound creates a set of standing waves. It creates a standing wave inside the rectangular box, and the periodicity depends on the wavelength of the ultrasound. So refractive index is now a function of the wavelength of the ultrasound. So if you put this expression of mu in the lambda and put back this lambda in the expression of A, then eventually you can see this is the phase retardation, this is the phase factor which is coming from the modulation of refractive index at different places of the liquid. That has a slightly complicated formula like twice pi delta mu being the maximum, this is being the amplitude of the change in the refractive index. Okay. So delta mu times L being the length of the box, and divided by lambda naught, that is our the wavelength of the light, and then the sign modulation 2 pi x by lambda s. This you see, this is essentially the phase of the light as it comes out. It's basically a periodic function of x. So the amplitude of this periodic function, let's call it V being 2 pi delta mu L by lambda naught. It's just a simple notation. Raman and Nagendra-Nath, their contribution, which they published several papers on it starting 1935, was to write the amplitude of the light in this form and then carry out the integration. So Raman and Nagendra-Nath, C.V. Raman and Nagendra-Nath, they showed that the angular spread of the angular position of the mth maxima, let's call it alpha m, is given by the sine of alpha m is equal to m times lambda naught by lambda s. Lambda naught being the wavelength of the light and lambda s being the wavelength of the ultrasound. Of course, m could be plus or minus depending on you will have maxima on both sides of the central maxima, and we give them numbers plus or minus depending on which side they are. Now, this is an important relation, and it helps us find out lambda naught if we know lambda s, and vice versa. Now, Raman and Nath, they also gave us the ratio of the intensity of different maxima. They found that Im by In, where m and n are the number of maxima, mth maxima divided by the intensity of nth maxima, that would be given by the Jm square V by Jn square V, where J is the Bessel function and Jm is the Bessel function of mth order and Jn is Bessel function of nth order. This is an important relation simply because the intensity ratio in case of Raman-Nath effect is very different from what you expect in case of the simple Bragg reflection. In case of Bragg reflection, you do have similar dispersion relation that sine alpha m is m times lambda naught by the spacing. Of course, instead of lambda s, you do have spacing between the reflecting layers because the Bragg pattern comes from reflection. But Raman-Nath is, remember, we just showed it's a continuous variation of the refractive index. In any case, we do not need to go into the theory. The working principle will simply keep in mind that the light, before it is incident on the box, it had a flat wavefront, and after it passes through the box, it has a corrugated wavefront. Depending on where it has passed the box, it will have different phase. This phase variation is periodic, and its contribution of this entire front at different part of the screen results in a set of maxima, and their spread, the angular position of the maxima, is given by the relations, and intensities are also given by Raman and Nath. Now, suppose we are doing this experiment. So we have this box, we have the ultrasound head, which is like a speaker, and then we created standing wave, we pass the light, and then light falls on the screen, and we find that it does not have sufficient spread. So what we do is we let it fall on a thin lens, and this lens amplifies the pattern, and then we place a screen where we get to see clearly the central maxima and then first maxima on both sides, second maxima, and so on and so forth. Of course, I mean, we need to know the wavelength of the, the focal length of the thin lens, and from there we can find out if we find, say, mth maxima on the screen at a distance d prime, then d, the actual distance of the mth maxima from the center, could be found using the thin lens formula. And once we know that, we know the distance of the lens from the box, so we can easily find out d, which is the length of the distance of the central maxima. And we can use the relation small d by capital D, and we can find out the unknowns. This is essentially the working formula. Now let us look at the setup a bit. Right, so here it is. We have a laser source here, this black black tube, and it is mounted here using some screws which help us align the laser, turn it this way or that way. Then here what you see is a box. This box is full of liquid, and at the right side of the box, using this clamp, we have ultrasound head attached to the box. So here we have taken the picture from the other side. You see the blue head of this table lamp. This picture was taken, this right picture was taken from the side of the table lamp. So what you see here, the clamp holds the ultrasound head very tightly to the side of the box. So if you switch it on, then you will have a series of standing waves inside the box, and the light is passing through these layers, and eventually there is a tiny lens here, and this lens amplifies the pattern, and the far side of the room has a screen on which the pattern is available. There are few other stuff that we use. Say, for example, this particular gadget that is lying here, it's basically a receiver. So the ultrasound head, it produces ultrasound, and we also have a receiver using which we can actually find out the wavelength of the ultrasound, and we'll discuss that. But before that, the ultrasound actually source has this appearance. It is a box where the amplitude of the sound and the frequency of the sound you can adjust. You can make a big high amplitude, high frequency ultrasound. So this box can produce frequencies from approximately 750 kilohertz to 850 kilohertz. We can't hear anything beyond 20 kilohertz, so it's a far above what we can hear. So this head connected to this box, and once you switch it on, adjust the amplitude, adjust the frequency, it's producing ultrasound. And this is the receiver, this tiny object. It basically catches this sound, and we can measure that. So what we do is something like this. We have the water inside the box, and the head is here. We keep the head tightly attached to the side of the box, so we have layers of water of different density and refractive index. But in any case, suppose we have the receiver here, and you can see at a distance delta L, the receiver is immersed in the liquid. So we have the head and the receiver, and there are certain number of wavelengths passing through. It does not have to be an integer. Now what we can do, we can monitor the waveform of the ultrasound source, and we can monitor what the receiver is receiving. So what we do is we monitor the two waveforms using oscilloscope, and what you see is the trace where we have exactly an integer number of wavelength between the source and the receiver. So as a result, the source and the receiver, both the waveforms are more or less there in phase. Now suppose we move it slightly away, the receiver, by say half a wavelength. Then what will happen? The phase difference between the source and the receiver will be pi. So they will be just out of phase, and that is what you see here. Okay. So if we can measure how much it has moved, so let's say call it delta L, small amount of movement, then this delta L would be equal to half of lambda of the ultrasound. But then it is too small. I mean, typically it would be some millimeter length, so it's very difficult to adjust that much. So what you do is you move the receiver and simply count how many times the received wave crossing the source signal. So which means how many wavelength you can calculate that just by looking at how many times this blue tip is crossing through the trough of this the yellow source waveform. So that way, once you count, let's say n equal to 10 or 20 or 30, from there you can easily find out from the length that is required to have a n crossing of 10 or 20, you can easily find out the wavelength of the ultrasound. This is how we measure the wavelength. Now, we also know the frequency, of course. I mean, you can see it here. I mean, like one example, when we were trying to do this, it had 796. 96 is visible, and this is 7. So 796 kilohertz, and if you know lambda, you will be able to calculate the velocity of the sound in the liquid very easily. So we do that. Now, the main part of the experiment. So we have this box, and here you can see the ultrasound head. So, I mean, if this is the box, the ultrasound head is on that side, as you can see in the image, and then you have stratified water, a different density, different refractive index, and the light is passing through it. Okay. So as light passes through, it falls on the lens, and eventually on the screen, this is what you get to see on the screen. The central maxima and both sides, first maxima, then second maxima, then third maxima. You see many patterns. It looks very clean. And we have also, some boxes with typically, I mean, these are 10 millimeter, 1 centimeter boxes. So you can actually count the distance between the maxima. I mean, we have a more precise way to do this. I mean, we'll demonstrate. So anyway, this is the screen where you see the final pattern. So you see, we already know lambda s, we calculated that. And now if we can find out the distance of the mth maxima, then more or less we're done. From there we can calculate the lambda naught wavelength of the light. But before that, we need to know the focal length of the lens, which is extremely simple and can be done using, let's say, a simple light source and a screen. And we have this rail. The lens can be moved. So what we can do is we can keep the the screen at one end of the rail and move the lens until the image of this filament is clearly visible. So that is one time when the screen and the lens, they are at a distance of the focal length of the lens. Then again, one can move the other way, and you can have another position of the lens, for which again you get a very clear image of the filament, but this time the lens is closer to the bulb. So from the position of this lens and the distance between bulb and the screen, which you are not changing, you can easily calculate the wavelength. As for getting the position from the Raman-Nath pattern on the screen, you can take help of the ImageJ software, which does the following. I mean, if you have the image of the pattern and then draw a line across the pattern, and then it gives you the intensity distribution along the line, and you can see, I mean, clearly the different intensity, different maxima, the central maxima and then first maxima both sides, second maxima both sides, and so on and so forth. You can see many. So in principle, I mean, after the calibration, this is already in a millimeter calibrated, so we can calculate the D from this pattern using the software. So once we know D and plot D versus M, and we know the capital D, it is the distance between the lens and the box, and we know lambda as we just found it, so we can easily calculate lambda naught. So this is essentially what is the goal, the way we have done this experiment. We set it up this way, and this is essentially the physics of it. Thank you.